Consider these two functions, y equals 4x and y equals 4x plus 12. Both of them have the same rate of change, 4 y boxes per 1 x box. For both of these functions, the derivative is the same. The derivative of 4x with respect to x is 4, and the derivative of 4x plus 12 with respect to x is also 4. Suppose we wanted to undo that derivative. We can integrate our answer to get the original function back. The integral of 4 with respect to x is 4x. The problem is both of those functions had the same derivative, and when we integrate, we get the 4x back, but we're missing the y-intercept. The solution is we just put it back. So this is what we call an indefinite integral. The indefinite has to do with the fact that we're unsure what the original y-intercept was. So to take care of this, we take our integral algorithm, the integral of x to the n dx equals x to the n plus 1 over n plus 1, and we add a arbitrary constant to it, plus c. That c represents the y-intercept that we were missing. Check out this family of graphs to the side. Each of them has the same slope. We know this because they're parallel, but they all have different y-intercepts. So what we would do is, in this case, we would say, all right, the integral of 4 with respect to x is 4x, and then we would add the c. And then for each of these parallel lines, we would just make the c a different value, ranging from minus 10 to plus 20 in these examples. In physics, you often have a set of context clues for a situation that tells you, or at least gives you hints as to what the plus c should be. We'll do a bunch of practice with this in class. I also want to do some practice with the concept of a definite integral. And let's start with a very simple case. Here's a function, y equals negative 4x plus 20. And what I want to do is compute the definite integral of this function within the specific domain 0 to 5. So we would write the integral of negative 4x plus 20 with respect to x from 0 to 5. We integrate by using the polynomial algorithm. So negative 4x becomes negative 4x squared over 2, and then the 20 becomes 20x. And then if we put in the upper limit of 5 for x, we get negative 50 plus 100 is positive 50, and then we have to put in the lower bound, and putting 0 in for x gives us a 0, and then our total here is positive 50 minus 0, the upper bound minus the lower bound, and that gives us positive 50 as an area. Okay. Next, let's do the same thing, but let's do from 5 to 10. So it's the same integral. The only thing I'm doing differently is I'm changing the bounds from 5 to 10. And when I put in 10, I get a value of 0. And when I put in the 5, I get positive 50. And then if I do the upper bound minus the lower bound, I get an answer of negative 50. And that represents an area. Okay. Lastly, I want to compute the integral for this function all the way from 0 to 10. Okay? And so I do the integral one more time. It's the same function, but I'm putting in 10 as an upper bound and 0 as a lower bound. So I get a 0. And when I put the 0 in, I get a 0. And 0 minus 0 is 0. So that represents the entire area. To check out what this physically means, let's graph the original function, y equals negative 4x plus 20, and make sure that in that graph we include the domain we're interested in, from 0 to 10. So I plot some points, and I draw my line, and then I want to draw in the areas that we calculated. So in blue, I'm doing the 0 to 5, which is the area here, which is a positive 50 units. And then in green, I'm doing the 5 to 10, which we saw came out negative 50, and that matches up on this graph. It's in the fourth quadrant and has this negative area. And then I'm hashing out in purple the whole thing from 0 to 10, and that's both of those areas. And again, that matches up really well with what the calculation said, because the positive 50 and the negative 50 together add up to 0. And so how we can sort of think about this is that for this function from 0 to 10, the net signed area, the vector area, is a total of 0, but the geometric area, the scalar area for the situation, is 100 units.